Hello everyone, this is Doug, and in this video we're going to talk about enamines. I'm just going to introduce you to what they are, what the mechanism looks like, give you a couple of examples, but not really use them in any syntheses. We'll talk about that in future videos. Start off with, though, just to remind you, enamines, right? You just ene like an alkene, so you're going to have something with a double bond like an alkene, but it has an amine on it, so enamine. So there'll be some sort of nitrogen on that alkene, right? It's kind of like an enol where you had an alcohol on an alkene. Enamines are when you have amines on an alkene directly attached to an alkene. So let's talk about these a little bit more. Right, so like I said, enamines are when you have an alkene with an amine on them, right? So here I have just a straight up amine. This would be a secondary amine because it has 1,2 groups on it, right? So this would be a secondary amine. Here I have a tertiary amine because it has 3 groups on it. This one over here, this would be my enamine, right? Because I have an alkene, right? Here's the alkene, and here's your amine. It only has sp3 things attached to it aside from being attached to the double bond, but it was an amine before it was attached. So this would be your enamine, right? Again, the ene for alkene, and then the amine for amine. And then lastly, I talked about this in the previous video, but right, I don't want to make sure that you get these, I don't want you to get these confused, right? This would be your imine, where you have an N double bonded to a C, that's your imine. So I-M-I-N-E. So you have amine, imine, enamine. This video is all about enamines, so let's talk about how do we form enamines. The idea is that you are going to form them right from usually aldehydes or ketones. So this first thing is going to be an aldehyde or a ketone. But what's really important is that on this alpha carbon here, so you have this alpha carbon here, you need to have at least 1 alpha hydrogen, right? So we need at least 1 alpha hydrogen. So alpha meaning, again, 1 away from some important functional group. In this case, our important functional group is the ketone or aldehyde, so 1 away from that would be the alpha. So that's the alpha spot. The other thing that we need here is we need a secondary amine. It has to be secondary. If it's a primary amine, this reaction will turn into an imine, which is more thermodynamically stable. If it's a tertiary amine, the reaction will not work. So tertiary amines don't do anything. They don't make amines, they don't make imines, and they don't make enamines. And then, of course, you're going to need some sort of acid catalyst. So you might see just H plus written out. You might see a specific acid like, sulfuric or something like that. And then you will form your enamine, right? So notice that I lost that alpha right here in this alpha spot. I no longer have that alpha hydrogen. It became part of water. And now I've attached my amine onto where that carbonyl was. So that's kind of the overview. Let's take a look at a specific example and the mechanism. So here's an example, right, where I have a, let me write this out here. So I have a ketone. We have 2 alpha spots. They both have 2 alpha hydrogens, so we know that'll work. And then I have a secondary amine, so I know that that will work. And again, I just take wherever that carbonyl was, so in this case it was the middle carbon, carbon 4, and I attach my nitrogen on there, and then I have an alkene going off into one of 2 directions. So let's take a look at the mechanism, see how do I know that that's what that's going to form? What does that look like? So I'm going to take my strong acid here and go ahead and split that up. Since it's a strong acid, that seems fair. So HSO4 minus and H plus. I'm going to go ahead and put my partial charges on things. So I've got a partial negative, I've got a partial positive. My amine has partial negatives and partial positives also. And then I have a full positive on the H plus. First step, that H plus is going to do something. You can either draw it going onto the amine or onto the carbonyl. It absolutely would be hanging out on the amine. That's totally fair. But we'll see that's not very productive. It's not going to get you any further. It's not going to help the amine add to the carbonyl. So you have a side sort of equilibrium going on with the amine and the acid. What really is going to be our first step that gets us somewhere is to do the protonation step. We're going to protonate our carbonyl. So first we'll protonate the carbonyl, which will give us this. So I have a positive charge there. You'll note that just like with the other video where we did the imine formation, that I have the same resonance structure. And what you'll see actually here pretty quick, and I'll mention this again, is that the really the mechanisms between the imine formation and the enamine formation are very similar. And the only difference is the last step. So you've taken your carbonyl and you've protonated it, making it much more electrophilic. Right now it has a full positive. And now what you do is now your amine can add into that carbonyl. Now that that carbonyl is much more electrophilic, it's much more electron deficient. So now your amine can add to that intermediate. I don't care if you have them go directly to the carbocation, or you could have had it gone to the carbonyl version of that, whichever resonance contributor you want. They're both fine. They're both saying the same thing. They're both going to get you to this, where you have, I want to kind of make this go down a little bit so we can get out of our way some. So now I've put those electrons up onto that oxygen, and now my nitrogen is the thing that is positive. And nitrogen has the hydrogen on it, it's positive. It might sit like this for a little bit, but the thing is, just like with the other mechanism, right, that the nitrogen is going to take back its electrons at some point in another equilibrium here, where now I've got the OH, and now I have the nitrogen here, and my freed up H+. And I'd have a hemiaminal intermediate. Don't worry about hemiaminal unless someone cares. I don't. So I have H+. I have these electronegative atoms, right? We said our oxygen's partially negative, our nitrogen's partially negative, so that H+ is probably going to go onto one of those. If I have the H+ go onto the amine, that's going backwards a step, so that's not really taking me anywhere. Let's have the H+ go on the oxygen instead and see if that gives us a new intermediate, if that gets us any closer here. So I'm going to go ahead and draw my alcohol picking up the hydrogen, which gives me an O with a positive on it. And then I still have my nitrogen here like this. Now we have seen this before here, right, where we said that the oxygen's not thrilled with being positive, and so it can do one of two things. It can take back electrons from a hydrogen bond, or an OH bond, I should say, which means I'm going backwards a step. That'll give us the previous intermediate. Or we can break that bond and water can leave, right? Water is a leaving group. And when we look at that, what we can draw here is a carbocation and ask ourselves, how stable is that carbocation? So let's take a look at that. Now we have this. Now my nitrogen is the only thing attached here. We have a positive, and we made water, so we have H2O. And you'll see actually that we're pretty close to our product already. This carbocation is secondary, which is really not that bad, but it's actually better than secondary because I can draw a resonance structure here, right, where these electrons from the nitrogen drop down and stabilize it. So let me draw the resonance contributor here. If we draw the resonance contributor, you'll see that you have a double bond N, and now the nitrogen is positive. But again, that carbocation is really stable, so it's easy for water to leave is the point. Now we're almost to our product, right? You may recognize this mechanism. This is almost exactly like the imine formation mechanism. For the imine formation, what we had over here on the left-hand side, we had a hydrogen on the nitrogen so that we could just remove the hydrogen and get to our imine. For enamines, when you use a secondary amine, you don't have a hydrogen on this nitrogen anymore. You don't have a hydrogen to kick off. So something's got to give. This molecule is a cation. It's positive. It's going to kick a hydrogen off of somewhere from something. And so what we're going to see, I'll draw this in like a different color just to emphasize it. What we see is that, remember I was saying how important it was that we had these alpha hydrogens, right? I had 2 here, and I had 2 here. You need at least 1 alpha hydrogen. This molecule is symmetric, so it doesn't matter which one I take. I will pick this one just so it matches my drawing up above. What's going to happen is basically it's going to look kind of like an elimination, where this CH bond is going to break. These electrons drop down to form that pi bond and kick these electrons back up onto the N so that it has its lone pair. And that will give us our enamine. We've regenerated our H+ catalyst. We made water like we said in that previous step. And so our acid catalyst can go ahead and react with another molecule, with another one of those parent carbonyls, whatever that carbonyl is, to form more enamines. And so every step of this enamine formation is reversible. You can go one way or the other. And just like with the imine formation, that other video, the real way to drive this reaction is that you got to remove water. You just remove water as much as you can. You try to keep it water-free either by adding a dehydrating agent like magnesium sulfate or molecular sieves, or you try to boil away the water if you can. If you choose your solvents right, you try to distill the water out. This is one of those reversible reactions. So if I want to turn my enamine back into my parent carbonyl compound, into the ketone, right? So if I want to take my enamine and I want to turn it back into the ketone here, to go backwards, right? All I need to do, if I want to go backwards, all I have to do is add a bunch of water and acid, and that's going to drive the whole reaction just backwards, just that Le Chatelier's principle stuff. So if you want to know the reaction, the mechanism for turning an enamine into a carbonyl, it's this exact one. You just go in reverse. That's the idea. You just go in reverse. You'd have your enamine, right, just to give you a little sampling. You'd have your enamine, these electrons would drop down, these electrons would kick out and go get the H plus to give you this intermediate again, and then you just keep on, like I said, just go backwards and backwards and backwards. You just do the exact opposite. So that's the mechanism, right? So really the big difference between forming an imine versus enamine is what type of amine do you have? Because if you start with a primary amine, you're going to go to the imine because you have a hydrogen to kick off at the very end. If you go with a secondary amine, you do not have a second hydrogen to kick off at the end, and so you're forced to form the less stable, but still fairly stable enamine product. So that's the mechanism. Let's look at these two examples here. Right, so here I have an aldehyde. I do have alpha hydrogens here. I have two. I just need one, but I have two in this case. And I do have a secondary amine. So all I really need to do here, right, is I just need to redraw my carbonyl compound. So here I have an aromatic ring. It looks like it's attached here. It was double bonded to the O, but now it's going to be bonded to the N. And the two things on this end apparently were methyls. So CH3, CH3. And since it's an enamine, now I need to have a double bond between what was the carbonyl and what is now the alpha carbon. So I need a double bond between those two things. Where's my carbonyl, there was my alpha. I could draw the CH from the aldehyde here still. It doesn't really matter because we tend to not draw CHs, but if I put the H's at those spots, that's what it would look like. And you could imagine you could get a mixture of products. Here I drew the Z, but you could have an E version as well. You could have the E version as well. Same thing if I look at this other one. Again, I have alpha hydrogens. It doesn't matter which side I pick from. I have a secondary amine. I switch the spots. It doesn't make it a different reaction. The idea here is that you have a secondary amine and you have a aldehyde or ketone. Here we have a ketone with alpha hydrogens. Ketone with alpha hydrogens. So that means I'm going to redraw my ketone. I need an alkene between the alpha spot and where the oxygen was. And then I put my nitrogen on here, and apparently this nitrogen was in a ring, so just leave it in a ring. You don't have to change anything. I know rings kind of freak people out, but it doesn't really change anything. And then in this last example here, right, so this would be the reversal. So this would be removing the enamine. Removing the enamine or turning it back to the carbonyl, right? So you're going to take this back and turn it back into whatever the parent carbonyl was, whether it was an aldehyde or ketone. And again, to do that, you just add acid and water, right? So like I said on that previous slide, to do the reverse reaction, you just add a boatload of water and acid, and it just unravels super quickly. It's usually very quick reactions. And so for this one, it looks like, well, here was my amine piece. So I'm just going to kind of redraw that. Apparently, the secondary amine that this came from was this. So here was my secondary amine. And it looks like the other part was the ketones. So wherever that amine was, wherever that nitrogen was, that's where my carbonyl was. So that's where my nitrogen was. There's my carbonyl then. And so those would be my two products. Now be mindful as far as how much acid there is. Normally I'd be fine with you just drawing these two products. However, technically if you're in acidic conditions, your teacher or your homework or whatever might be expecting, excuse me, I lost a carbon there, might be expecting you to protonate your amine as a product. Since you're in acidic conditions, the amine might be protonated still. So however you want to draw the amine, whether it's in the basic form or acidic form, you get that 6-membered ring with the nitrogen in it, and you get that ketone, right? This is your parent compound back. So these are reversible also, like we talked about in class, right? Both the imine, the enamine, and the acetal all just reverse back to the carbonyl in the presence of water and acid. So I hope that gives you a starting point. Definitely, read some chapters, review your notes, do some practice problems, study up. If you have any questions or comments, please let me know. Happy studying.